Learning target 1.2 is mass spectroscopy of the elements. Spectroscopy basically means you're measuring something that's in a spectrum. So you can have, variable amounts of values. It's not set in discrete intervals. We're still on the mole enduring understanding, so that's great. Explain the quantitative relationship between the mass spectrum of an element and the masses of the element's isotopes. I should probably talk about what isotopes are, just in case you don't know. So if you've ever wondered why carbon has 6 protons and 6 neutrons, and each of these things have a mass of 1, right? But carbon on the periodic table has a mass of 12.01. It's not exactly 12. That's because this isn't the only type of carbon there is. There should be an atomic number in the box too. That's 6. This tells you how many protons there are. That can never change. What can change is the number of neutrons. And if the number of neutrons change, since a neutron has a mass of 1, the mass of that entire element is going to be different. So if carbon has 6 protons, and if it's carbon, it will always have 6 protons, but it has 1 more neutron, it's got 7, this will have a mass of 13. So this has a mass of 12. This has a mass of 13. The way that we indicate those is like this. There'll be a little number there. 12. 13. There is carbon 14 too. What this is it's an average of all of them. If you notice, the average of 12, 13, and 14 is not 12.01, it's 13. So it's not an absolute average, it's a relative average. So this means that of all the carbon atoms in the universe, most of them are 12. There's a little bit that are more than 12. 0.01. That's why it's a little bit more than 12. Those are isotopes. I think I did a good job. We'll see. Okay, great. This is a mass spectrum. So they took a sample of zirconium. Since this zirconium has more than one isotope, they put it through the machine. The machine's complicated. I'll explain it in class if you really care. But what it did is it separated the zirconium isotopes based on their masses. So most zirconiums have a mass of 90. Some of them have a mass of 91. Some of them have a mass of 92. Some of them have a mass of 94. Some of them have a mass of 96. You can use the y-axis to estimate where it actually is. Hopefully on the AP test, there's actual grid lines in the graph so that it's easier to read, because there's no way I would be able to tell that it is 51.5. Looks closer to 60 to me, but what do I know? Anyway, that's what all that says. So 51.5% of zirconium has a mass of 90. So what you can do is you can use these data to figure out what the average mass is, and that should match the periodic table. So that's kind of a hint that you did it correctly. So the way I would do this is I would change these percent abundances into relative abundances, fractional abundances, so make them out of 1. So 51.5 becomes 0.515. Then I would multiply that by the mass, so 0.515 times 90, zirconium 90, and then add them all together. Where should I do that? Because I didn't really give myself any space to write. So the first one, 0.515 times 90, plus the next one, 0.112 times 91, plus the next one, 0.171 times 92, plus, I'm going to move down here, I ran out of room, 0.174 times 94, plus 0.028 times 96. Throw that in the calculator. Left mine on the desk here. Need sunlight. There we go. I mean, you could cheat and just look at a periodic table, but whatever. This works too. Hopefully I put that in right. I got 91.318 grams per mole, probably, is the unit. Great. 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 They say it's on the carbon-12 scale because what they did is they took carbon with exactly 6 protons and 6 neutrons and made sure that weighed exactly 12 AMUs. And then everything else is based off of carbon. So that's what the carbon scale is. If you're curious, you don't need to know that for the test. Okay, that was fun. The mass spectrum of a sample containing a single element can be used to determine the identity of the isotopes at that element and the relative abundance of each isotope in nature. So that's basically what we just did in mathematical format. Basically, the equation that I wrote on the board with the parentheses and the times and the plus, any one of those pieces of information can be the unknown, and you just need to rearrange the equation and solve for it. I trust that your algebra skills, you can handle that. You are not, so this is again from the document, and specifically sometimes teachers overteach a certain topic and then the kids get worried because it's really hard and difficult. So this is just letting you know, reassuring you that this piece that is usually hard and difficult is not actually going to be tested, but it is a part of the learning target. So it says interpreting mass spectra of samples containing multiple elements or peaks arising from species other than singly charged monatomic ions will not be assessed in the AP exam. What the heck does that mean, kids? Do you know? I'm trying to get, there it is. This is just zirconium. So it's just a single element. You can throw any sample of matter into one of these machines, a mass spectrometer, and it'll break it apart by weight. So if you put water in it, it's going to show you different hydrogen peaks and oxygen peaks in the same graph. What this is telling you is that you won't see those on the AP test. It'll just be a single element, which makes your lives easy. And then this is mathematically what I did. They do it a little bit differently. Instead of changing it to fractional abundance, they leave it as a percent abundance. So the 51.5 I changed to 0.515. They didn't, but then at the end, they had to divide by 100. So whichever way you choose, I don't care. I have a preference. You probably do too. So whichever one you want to do. And I think that's it for this learning target. Nice and short.